Okay, next topic. And so we're about halfway through chapter 2 of Journal 3.5. We're going to talk about curvature of vector functions. So we're going to use this notation, k of t. So a vector function, like the one here, this is a space curve, a nonlinear space curve in R3. And we're going to be able to figure out how curvy that curve is relative to other points on that space curve at a particular time t. And in this example, we're interested in that at t equals 1. And we're also going to be able to calculate something called the osculating circle and its radius. And it turns out that the radius of the osculating circle is inversely related. So once you get the curvature, you take 1 over that, and that's the value if the curvature was negative. And that'll give you the radius of this thing called the osculating circle. Well, let's think back to make a few analogies and extensions. So think about back in R2, y was a function of x. The tangent line we also talked about, besides just being a direction of motion, it was also the best linear approximation to the function near the point of tangency. The further you got away from the point of tangency, the more area you had, but if you zoomed in close enough, you could actually think about the nonlinear function is made up of a bunch of little linelets, little teeny line segments, and those line segments did a really good job estimating locally the actual nonlinear curve. And so a tangent line is a best fit line near the point of tangency. Well, now we're going to ask ourselves, for something nonlinear, besides just approximating a nonlinear thing with a linear thing, could we approximate a nonlinear thing with another nonlinear thing? So there's several ways you could do this, and we're only just talking about this one, but that's a whole other field of cubic splines and interpolations, a whole other, you can take graduate classes and this sort of stuff. But we're going to try to approximate a nonlinearity, a nonlinear vector function, or a plane curve, or an explicit function with the best fit circle. So that's a nonlinear thing. So we're going to approximate a nonlinearity with a specialized type of nonlinearity, a circle. So it's going to turn out that the osculating circle is the best fit circle to the curve near the point of tangency. Best fit circle to the curve near the point of tangency. Okay, yet another review thing over here in this little box in the corner was to say you've probably already seen curvature, might have been briefly introduced in Calculus 1, maybe, and towards the end of that. If y is a function of x, there was this curvature formula, which involved the second derivative, and then first derivative, squaring things. And so probably your teacher could only give you really basic y is a function of x to compute the curvature for by hand, because they got messy really fast, even back in R2. And we're going to see the same thing's going to happen here in R3. Really interesting curves like that flies space curve. Not a crazy curve, but the vector function that described that curve had some you could never do a curvature for that hand. It's just a mess, tedious work, but we could do some ones like this. So you'll see that if I'm going to ask you to do one of these by hand on the final exam and midterms or anything, they have to be pretty basic to do them, because you'll see even this one gets a little messy as we go, and this is a very basic one. But your challenge problems and more interesting ones that you'll see in your careers and your majors, probably going to require some sort of numerical tool to help you. Okay, so before we get to this and visualizing this space curve, I want to talk about the curvature formula for us in R3. So this is now in R3. What we need is in this box. The curvature formula in R3 is we are going to take our unit tangent vector t, take its derivative, then get the length of that, and divide it by the first derivative of the function, which is also the velocity get the absolute value of that, or sorry, the magnitude length of that. Denominator actually represents the speed, right? We call that the speed function in the earlier lesson. And the numerator is the rate of change, the length of the rate of change of the tangent vector. Remember, the t is the unit tangent vector. That's the direction of motion normalized to have length 1. And so I want to just show you on these two curves here, and we'll put this one in blue is the clearly less curvy, right, of the two, sort of a slight bend. And then the second one, much curvier road if you're traveling on this on your motorcycle. And we want to stop at 2 points of tangency. Let's stop at the first one, t. Then we'll go a little further away, some distance delta t away from that. And we try to make that distance about the same on each of these. So from t to t plus delta t, let's look at these purple vectors. Again, CalcPlot 3D, we looked at those purple vectors were the capital T's, the directions of motion. And here, this purple vector, where we go, when we stop at t, we would sail off in this direction. We'd go a little further along this curve, and we'd sail off in this direction. Now, what we notice about those two purple vectors is they're not too far apart from each other. In fact, when I move this one up so they both have the same initial point, I'm looking at these two vectors. Their angle between them isn't too far. So the change in t, which is also going to be denoted by the rate of change when you take a derivative of something, isn't too far. As opposed to this example where the road was much curvier, I did the same thing. I got a direction of motion at the first point of tangency. I went a little further along, got a direction of motion that pointed me down. And now I looked at the difference between those two, and I'm here and here. And those are quite different, right? The change in those directions, from here to here, I shifted that one over. The change in those directions, the rate of change of the tangent, unit tangent vectors, capital T, so delta t, which is also the same as taking a derivative, t prime, that is quite far apart. Wasn't much here, quite a bit here, but that's because this road is much curvier. And so that's to give you an idea of the derivation of the curvature formula. So maybe it's less to memorize because you're thinking about what am I doing? I'm changing, I'm looking at the rate of change of my direction of motion as I'm traveling along that curve. This can be actually, we haven't gotten to this yet. This denominator is actually related to arc length. We haven't gotten there, we will. But you can also think about it as I've traveled a little bit along this road. So I go just the same distance on the not so curvy road, the kind of straight, slight bend, to the really bendy road, and that is magnified. Okay, so that's the derivation, that's the idea behind it. And now we're going to make some space and actually do this problem by hand, and then we'll check it with a tech tool. First off, do you recognize anything about this space curve? Well, notice that the third component, we're actually always at a height of 2. No matter what happens in the x and y, we stay at a z of 2. So we're actually taking a space curve, which actually ends up being a plane curve at the z equals 2 plane. Z equals 2 is a horizontal plane. We're fixing ourselves, this has to live always in that plane. So really we just have this parabola, which would be a parabola in the xy plane. R of t equals tt squared is just this parabola hugging the y-axis. But when we go to 3 dimensions, it's shifted up 2 units. And it's in the z equals 2 plane. And this is now a space curve because it has 3 components, but it lives always in the z equals 2 plane. And then we want to know when t is 1, what happens. And so the point of tangency happens when t of 1 is plugged into the function and you get a value of 1, 1, 2, oops, which is also a point. So that's the terminal point of the vector, 1, 1, 2. So that would be the point 1 along the x, 1 along the y, and 2 something like here. This is when t is 1. And we want to know what is the precise curvature there. Usually it's more interesting though, you don't just, textbooks throw out a number like this. They say, oh, at t equals 1. But usually you want to say, how does that compare to say at 0 or at 5, right? We can tell when we get up here at 5, it looks like it's going to be more linear. So it should be less curvy. And then at 1, and maybe even more curvy around 0. So usually that's what you're going to do, is you're going to compare a couple values, and or further, you'll do this on a couple problems, maybe even a challenge. Where's the maximum curvature? So you find the maximum curvature, then you're if this is a road, you might want to know where to put guardrails. But maximizing the curvature function is messy because already the curvature is messy, which again we'll see for this problem. Okay, so curvature, here's our formula. First we need to get derivatives and lengths. So let's start with r prime of t. No problem, 1, 2t, 2. Evaluate that at 1. That's where we're interested. R prime of 1 gives the direction of motion. And that'll be 1, 2, 2. The length of that is the square root of the sum of the components squared. So that's 4 plus 4 plus 1 is 9. Square root of 9 is 3. Oh, that worked out nice. That's our denominator then, because we're trying to get k of 1. So we want 1, 1, 1. All right, so we have part of this, but we now need to get the numerator of our curvature formula. And so that is going to require that we get first the tangent vector at any t, and then we'll take that derivative. So remember with the tangent vector, the definition of that is just your direction normalized. So that is r prime of t over r prime of t magnitude. And we want that at 1, so we want t of 1 is then r prime of 1 divided by the length of r prime of 1. And so we get this vector divided by 3. So 1/3, 2/3, 2/3. That is the direction of motion normalized to have length 1. And now we need to take the derivative of this at any t. Oh, so let me go back here and actually put this in this notation. This is 1, 2t, 2. Let's write it generally for any t. And then the sum of the components squared will be the square root of 1 plus 4 is 5 plus 4t squared. Oh, actually, I think I see an error I made up here in my derivative. Let's come back up here and check. Here's our space curve. Take the derivative. This should be 0, right? Derivative of the constant is 0. This should be 0. This would be 0. That means this would be square root of 5. This would be, actually we didn't even need that part. We really just needed to get down to the, so 1 plus 4t squared square root. Better? Okay, so that is our direction of motion shrunk to have length 1. And now we need to take the derivative of that. So let's maybe clean this up a little bit before we take the derivative and write it this way. The denominator is to the 1/2 power. It crosses the bar, it becomes to the minus 1/2 power. So this is going to be 1 plus 4t squared to the minus 1/2 in the first component. The second component will be 2t times that. 1 plus 4t squared to the minus 1/2. 0 in the last component still. Okay, that is the unit tangent vector, but now I need to get its rate of change by taking its derivative and then get its length. So some more derivative work here. Just a general power rule, then I need a product rule in the second one. So let's t prime of t is going to be times the power down a power, so minus 1/2 times the derivative of what's inside times an 8t. So minus 1/2 times 8t is minus 4t. What's in parentheses? Down a power. That's just the first component. We need some space to put the product rule, and we know the last component is still 0, derivative of 0 is 0. So in this second place, we need to take the derivative of the second component, which is a product rule. There's really a first function times the second function. So we'll have the first is 2t times the derivative of the second function. Well, we already did that, so I'm just going to copy that right here. So minus a 4t times 1 plus 4t squared to the minus 3/2. So that was the first function times the derivative of the second function. Oh, times the derivative of the second function. First function times the derivative of the second function plus the second function times the derivative of the first. No problem, it's just a 2 times this thing plus 2. 1 plus 4t squared to the minus 1/2. No sense in simplifying just yet. Let's just leave. Maybe the only thing we want to simplify is right here. That's a minus 8t squared. Okay, this is the derivative, but we need to evaluate that at 1. We need to get t prime of 1, which will be a vector. And then we need to get the length of that. And then that is finally our numerator. We already have our denominator is square root of 5. We need to get this numerator. And so I just want to show you something about, this isn't too bad to do the evaluation plugging in, 1 isn't a bad number to plug in, but I do want to show you a tech tool that may help you with your challenge problems. So if we go to Wolfram Alpha, we already did all the hard part of taking this derivative, but again, you could ask Wolfram to do this as well, to take, compute the derivative of this thing here, if you wanted, but we already did that. So let's just ask it though to evaluate this function. So we're gonna put in a vector function here, something, comma, something, comma, something, equals at t equals 1. So we're gonna put in our derivative, and then we're gonna ask it to evaluate that at 1, just so we don't have to do the arithmetic or to check our arithmetic. So the first component was minus 4t times 1 plus 4t squared, all up to the minus 1.5 power. Check that that first component is correct, minus 4t, 1 plus 4t squared to the minus 1.5. Yep, okay, the next component is minus 8t squared times 1 plus 4t squared up to the minus 1.5 again, plus 2 times 1 plus 4t squared to the minus 0.5. Last component is 0. Okay, we should expect a vector output, which it does, gives us this vector here. One nice thing about Wolfram 2 is you can click on the results, and it'll now show that as a vector, which is nice for the next step if I wanted to actually get the length of that. So if you still want to save, tedious calculation of the sum of the components of this squared, It's not back as 1 of 0, but still those are decimals and you don't have to type those in because they give me the vector length of that. Okay, and it treats it as vector, it gives the length, shows the picture. So 0.4 is our length. So we're down to this line now. We just got a length of 0.4. Oh, let me stop the screen share. So again, just showing that you can do some of the tedious calculation. You can do some by hand. You can also check your derivatives. You can ask it to do the derivatives and check. And now we're to here. So that is some decimal, what, 0.4, and that's like 2 point something. So probably a little less than 0.2-ish. You can get a value, and that's showing you exactly how curvy you are at 1. But again, usually that doesn't mean much until you make it relative to something else. So you might compare the curvature at several points along the curve. Maybe they're uniformly spaced if it was like that challenge problem where we had a ski slope that was shaped like a cubic function. You could get it at evenly spaced points along there, find out how curvy it is, figuring out of those 10 points that you chose, which one's curvy, has the most curvature. And then the last thing, so we got a curvature of 0.4 divided by square root of 5, whatever that decimal is. But the radius of the oscillating circle, no more work here. That is just 1 over that. So you're just flipping it. The radius has got to be square root of 5 over 0.4. So maybe a number a little bigger than 5. But one last thing then, let's check, see what Calcplot3D can do for this. So Calcplot3D also has some nice visualizations. Let's go enter our space curve, which was 2, which t squared, and then 2, which we knew lived in the z equals 2 plane. Let's check that. Yeah, we said it would be a parabola, but it would just be forced to be in the z equals 2 plane. We see that there. You could even graph the z equals 2 plane to check that the red one lives there. Let's turn on and turn off certain things. So we've already talked about tangents and unit tangents and normals, no problem. Maybe let's put now the osculating plane and the osculating circle and the curvature value. So Calcplot, here's another instance where Calcplot3D can do some calculating for you. And you can animate things as you go. So the osculating plane is not so interesting in this example because it lives in the z equals 2 plane. That's the little yellow plane that's moving as the point of tangency is changing. But notice the osculating circle is the best fit circle. And the best fit circle, as we get further away from the origin where the space curve gets more and more linear, starts having like a huge radius, right? Because it's actually looking more like a line. The surface is looking, or the curve is looking more like a line there. The curvature is getting smaller, but that means the radius is 1 over that. So in this case, right where I've stopped now, around t equals 2.76, the curvature up here in the corner is 0.01. So the radius then is about 100, right? But if I come back closer to the origin, keep trying to move that point on there, the point I move over here with the slider. To get closer to the origin, when t gets like, here's t about a half, a third, closer to the origin, the curvature value is getting higher, and therefore the radius is getting smaller. So the key moral is that the tighter the osculating circle, that's this black circle, the curvier it is, because the inverse relationship. So I just want to change one last thing here. Let's make this a little more interesting and maybe make this like e to the minus t or something in the third component. So it isn't forced to be in a plane. Now watch the osculating plane as you move. It changes, right? That yellow one is changing its angle as I'm moving through this. And the osculating circle is getting bigger when you're getting closer to linear, smaller and tighter when you're more nonlinear and closer to a circle. Okay, that's it for the first half. And then next week we do a couple more very interesting applications of extending from space curves to surfaces in space. All right, have fun with this week.